Okay, back to functions. We will show a nice structural result today that says simply knowing that there is a function between two sets that has certain properties tells us something about the sets themselves, which is kind of amazing. Like somehow the function is a fingerprint of the structure of the underlying sets. We also left a few loose threads last time. Like, for example, we talked about functions being invertible. Does this mean that there's some sort of inverse function floating around? Spoiler alert, yes, it does. That and more coming up in today's lecture. Recall our definition of function, domain, and codomain, which we put here. Also recall the definitions of injective, surjective, and bijective. Here's an important theorem. Let A and B be finite sets. Then the following are all equivalent. Number 1, the size of A is less than or equal to the size of B. Number 2, there exists a function f from A to B that is injective. And number 3, there exists a function g from B to A that is surjective. Now note, saying that these are all equivalent means that if one of them is true, all of them are true. Conversely, if one of them is false, all of them are false. Now to prove this, we can take a couple of different approaches. This textbook first shows that 1 implies 2, then 2 implies 3, and finally 3 implies 1. This makes a closed loop and means that we can get from any one of these statements to any other of them. Therefore, any one of them implies another one of them, and they're all equivalent. This is a perfectly valid way to do it, and this is probably the most efficient way to prove these things. But to add a little more clarity, we're going to do something different. We're going to show directly that 1 if and only if 2, and 1 if and only if 3, meaning that we'll show 1 implies 2, 2 implies 1, 1 implies 3, and 3 implies 1. That's not the most efficient, but it is the most straightforward in terms of the arguments. If you prefer the more efficient route, you can always look at the text. Okay, now we prove that 1 implies 2. Assume that the size of A is less than or equal to the size of B. Let us say the size of A is the number m, and the size of B is the number n. Let us write the elements of A as A1, A2, all the way up to AM, and the elements of B as B1, B2, up to Bn. Remember, we are assuming that m is less than or equal to n. So let's define a function. For all I from 1 to m, define f of ai to be bi. So f of a1 is b1, f of a2 is b2, etc. Notice that each different ai gives a different f of ai, and therefore f is adjective. We've done it. Now we're going to show that 2 implies 1. Let's assume that we have an injective function f from A to B. Again, let us say that the size of A is m and the size of B is n. But note, and this is super important, we are not assuming that m is less than or equal to n. That's what we're trying to show. Now label the elements of A as A1, A2, all the way up to AM. Now define the elements of B as bk equals f of ak for k equals 1 through m. So b1 is f of a1, b2 is f of a2, etc. Now since f is injective, the bk's are all distinct. That means that the set B contains at least m elements, because we've written down m distinct elements, and therefore the size of B is at least as big as the size of A, which establishes 1. Now we show that 1 implies 3. Assume that m is less than or equal to n, and again, we label the elements of A as A1 up to AM, and the elements of B as B1 up to Bn. Define g of b1 to be a1, g of b2 to be a2, all the way up to g of bm. Now there may be other elements of b, because b can be bigger than m, but let's just send them wherever we want. So for example, for any index bigger than m, just send g of bk to a1. It's not really going to matter. Because notice that every point in A has now been hit by some value coming out of the function g, and therefore g is surjective, right? We don't mind that we've hit multiple points twice or 3 times. We just want to make sure we hit every point once. Now finally, we improve that 3 implies 1, so we assume that we have a surjective function g from b to a. Again, let us say that the size of a is m and the size of b is n, but note again, we are not assuming that m is less than or equal to n. That's what we're trying to show. Now label the elements of b as b1, b2, all the way up to bn. Now consider the set of elements g of b1, g of b2, all the way up to g of bn. These all lie in A, and moreover, since g is surjective, by assumption, this set completely covers A. But note, this means that A can have at most n elements, because it's covered by n elements. It could have fewer if some of those are the same, but it doesn't have more. Therefore, we've proved that the size of A is no larger than the size of B, and we are done. Now we have a very important corollary of the last result. Theorem. Let A and B be finite sets. Then A and B have the same size if and only if there is a bijection from A to B. Note we're saying 2 things here, is that if 2 sets have the same size, there exists a bijection, and if there exists a bijection, they have to be the same size. Again, let me stress, we're only talking about finite sets here. Let's prove this. Let us first go from left to right. Let's assume that the size of A and the size of B are equal, and let's call that number n. Let's write out the elements of A as A1, A2, up to AN. Now, the size of A is equal to B, which of course means the size of A is less than or equal to B, and the previous theorem tells us that there is an injection f from A to B. So let's apply f to this set A, and we get f of A1, f of A2, all the way up to f of AN. Because f is injective, these points are all distinct. If these are all distinct, then we have obtained n different elements of B, and by assumption, B has exactly n elements. So this function is also a surjection. Therefore, it is a bijection. Now we go from right to left. Assume that there's a bijection f from A to B. Since f is injective, by the previous theorem, this implies that A is less than or equal to B in size. Since this function is surjective, that implies that B is less than or equal to A, right? We're using the previous theorem, but with the roles of A and B reversed. And if A is less than or equal to B in size, B is less than or equal to A in size, then A and B have the same size. Okay, now we're going to talk about the composition of functions. Let f be a function from A to B, and let g be a function from B to C. Then we can compose these 2 functions by first applying f and then applying g. This gives us a new function from A to C, which is called the composition of these 2 functions. We typically write this composition as g circle f, and the circle symbol will always imply composition. We can also write out the action explicitly by saying g composed with f applied to the point x is g of f of x. One point. It might be a little bit confusing that the functions seem out of order. We do f first and g second, but when we write the composition, we write g first and then f. Okay? But this is because we apply functions on the outside. So as we apply more and more functions, we sort of move leftward instead of rightward. Just the way we denote functions. So the order is, in some sense, backwards. Another point, and this is one thing to really pay attention to be able to compose functions, we are required to make sure that the codomain of f matches the domain of g. We can now state and prove a nice theorem about compositions. Let f go from A to B, and G go from B to C, and consider the composition G composed with F from A to C. Then, number 1, if F and G are both injective, then so is their composition. Number 2, if F and G are both surjective, then so is their composition. And number 3, if F and G are both bijective, then so is their composition. Basically, if F and G are both X, then the composition is X, where X is any of the 3 properties, injective, surjective, or bijective. First, let's prove part 1. Assume that F and G are both injective. Now choose X and Y in A with X not equal to Y. Because F is injective, that means F of X does not equal F of Y. But since G is injective, that implies that G of F of X does not equal G of F of Y. So what we have shown is that if X does not equal Y, then G composed with F applied to X does not equal G composed with F applied to Y, meaning that G composed with F is injective. Now let's prove part 2. Assume that F and G are both surjective. Let Z be any point in C, and we need to show that there's an X in A such that G composed with F applied to X gives us Z. Well, since G is surjective, we have a Y in B with G of Y equal to Z. Since F is surjective, there's an X in A with F of X equal to Y. Therefore, G of F of X equals G of Y, which equals Z. And we're done. Finally, part 3 is just parts 1 and 2 put together. Okay, so now, why do we call invertible functions invertible? It's because these functions can be inverted. They're invertible, able to be inverted. Let us be precise with the following theorem. Let F going from A to B be a bijection. Then there exists a function G from B to A such that G of F of X is X for all X in A, and F of G of Y is Y for all Y in B. This function is called the inverse of F, and sometimes denoted F with a -1. Okay, here's the proof. Let F go from A to B be invertible. Then for any Y in B, there is exactly one X in A such that F of X equals Y. Remember, since F is surjective, there's at least one X, and since F is injective, there's at most one X. Put those together, there's exactly one X. Since there's exactly one X that maps to Y, let us define G of Y to be that element X. And then we can check. F of G of Y is F of X, which is Y, and G of F of X is G of Y, which is X. Recall the example we considered last time. Take the function F of X to be X squared. As we said before, if we think of this as a function from the reals to the reals, this function is not invertible. It is neither injective nor surjective. But if we take our domain and codomain to be the non-negative reals, then F is bijective and thus invertible. And as we know, the inverse of this function, X squared, is just square root of Y. And we can check. F inverse of F of X is F inverse of X squared, which is the square root of X squared, which is X. Remember, X is non-negative, so the square root of X squared is always X. And moreover, F of F inverse of Y is F of the square root of Y, which is the square root of Y squared, which is Y. Now let's revisit another function from last time. Let's take the set A and B both to be the numbers 0 through 9 and consider the function f of x equals 7x mod 10. As we computed before, each number appears exactly once when we apply the function, and therefore the function is invertible. Let's compute the inverse by reordering the outputs, we see in this table here, and if we look closely, it looks to us like the inverse function, f inverse of y, is 3y mod 10. So let's see if this holds up. Notice that 3 times 7 is 21, which is 1 mod 10. And so we have f of f inverse of x is 7 times 3x mod 10, which is x mod 10. f inverse of f of x is 3 times 7x mod 10, which is x mod 10. So this works as an inverse. So in this sense, we can actually say the multiplicative inverse of 7 modulo 10 is 3. Another way of saying this is that if we'd like to divide by 7 mod 10, that's kind of the same as multiplying by 3 mod 10. So if you remember, when I said at some point that we don't divide modulos, well, that's not exactly true. We can sometimes divide modulos. Not always, but sometimes, as we see in this case. Okay, I will stop there for now.